Thank you, Daniel. Thank you, Gillian. Thank you to the Malta Café Scientifique and the Spazio Creative for this, the opportunity of this chat, but especially a great thanks goes to you to be here. So there is actually someone to speak with. Great. And we will speak, as Daniel said, about quantum cats and future technologies. Now, you may wonder, what do cats and quantum mechanics have in common? Well, the first thing is that I love cats. The second, and most importantly, that Schrödinger loved cats. And he was worried about the fate of his beloved cat, because if the laws of quantum mechanics would climb up from the microscopic worlds of atoms up to the microscopic one where the cat, his cat was living, then there would be some ridiculous case, as he wrote in his paper. Now, in what it is ridiculous? In the fact that, let's take Schrödinger's cat. We put him in a box, in a sealed box, and there is a vial containing poison, over which looms a hammer tied to a lever, which is connected to a Geiger counter close to a radioactive atom. So if the radioactive atom decays, the Geiger counter detects it, the lever goes down, the hammer breaks the vial, the thirsty cat drinks the poison and dies. If the atom does not decay, then the cat is thirsty but alive. Now, where is the paradox? That in the microscopic world that of atoms, there is another possibility, and it is that the atom at the same time decays and does not decay. So if this somehow ambiguous situation would climb up all the levels of reality up to the microscopic world, then the Geiger would click and not click. Then the lever would be up and down at the same time. The poison would be in the vial and on the floor at the same time, and the cat would be at the same time dead and alive. And this is actually a bit of a paradox. So, there are two levels of reality, somehow. One is the classical world, the one that rules the motion of sun, planets, us, macroscopic world. And then there is the world of quantum, of microscopic things. So, photons, electrons, atoms, where the laws that rule their behavior are completely different, and these two worlds are in contradiction with each other. So, what we will do tonight is to cross this border in one direction, but as in the other one, looking if we can take some properties, some characteristics from the quantum world back into our microscopic world and use them for some technological device. And then comes in the future technology. That is not future, it's actually already here. So, but science, physics is an experimental science. So, what we will do are experiments. 3 experiments, and you, because you have to be involved, are asked to guess the outcome of the experiments. They are quantum experiments. Now, I was not able to bring with me clearly all this instrumentation, and we will focus at the beginning only on this part. What is depicted here? It's a typical quantum optics experiment. We have a laser, something like this, a bit more powerful. There is a beam of light, and somehow it, with mirrors, it enters this square. We will first focus just on the square. Now this is the laser. You see also the beam, right? So you see the point and you see the beam. In case you do not see the beam, what we can say is the following. I guess that if I see a point there, then the beam has traveled from here to there in a straight line. But if you do not believe me, I have a very high-tech instrumentation with me, with which you can actually see the beam. I use it every day, and it's this one.
You want me to switch off?
No, we don't need it. So you see a point, but you do not see the beam. Now you see the beam, right? Because somehow I'm increasing the scattering of light of this beam. So I'm sure that if it goes there, it travels along this line. Good. Now, we say, I send the light, because we are going to build up this square. This is the laser beam, and then here is a kind of a small cube. What does it do? It's a beam splitter, something like this. And it does a half silvered mirror. What happens is that if I input light here, half of the intensity, let's see, goes there, and half is here. If you don't believe me, I can take again the... so you see that we can safely say that if there is a spot over there, it means that here is a beam and here is a beam of light. I hope you see it. It's half of the intensity, so it's less bright. Good. So I send the laser, half of the intensity goes here and half here. But this is optics. Now let's go to quantum optics. Quantum optics means that I start, suppose I were able to reduce the intensity of this beam to just one single photon. A photon is a particle of light. It's an elementary particle. So a particle of light, elementary, cannot be divided. So if I send here a single photon, it cannot go half this way and half photon this way. So how do we do the experiment? Now we can do it with the laser, but we put a detector here and a detector here. So this beam splitter, half of the time transmits the photon and it's detected by D1, and half of the time reflects the photon and it's detected by D2. So what I can say is that if I get a click by D1, then the photon has been transmitted to the beam splitter and has followed the green path. If it is detected by D2, it has been reflected and has followed the red path. So if I send 100 photons, 50 on average are detected by D2 and 50 by D1. Very easy, right? Now, we build up this square here and here, and these are just mirrors. So the role of these mirrors is just to bend the light so that they converge again. What happens? Well, here's a mirror. If this one clicks, single photon, then it has done the green path. If this one clicks, the photon has done the red path. Very easy. Now we put another beam splitter, identical to this. So if I take this, alone this, send laser, half the time the photon goes left and half the time goes straight. And we put it here. We have all our situation in mind. Now, the first question I wish you to answer is, how many particles are detected by D1 and how many by D2? So I send, say, 100 photons, one at each time. How many end up here and how many end up here? So let's say 1 minute. Can you do it? I don't know how to do it. Sorry, because there is. But
so you are going to use your mobiles basically, and you are going to go on kahoots.com, right? .it, sorry. So if you go on the website kahoots.it, so KAHOOT, and you will be given a code, and you will be able to answer the question quite soon.
Okay.
In the meantime,
what was it?
KAHOOT.it.
Okay.
So what is the pin?
Okay, what can I do?
You want to go to the IT? Yes. Just for
it increases the tension.
So it's 411643. When you sign up, you don't have to log in. You just need to log in.
But then we can use the question with the answers or with the answer, with the possible answer. Okay, thank you. Okay, this does not count as time. No.
Is everyone in? Yeah? Okay, so let's see what your answers are.
No, you start.
You have to start again.
No, don't press that. Press
I'm not
start.
getting a start, alright?
But they don't see the answers.
I think when you log in, you have to press start.
They will just see this A, B, C.
Okay, they see something.
Yeah, you press start.
Below again.
Teachers there.
Beautiful.
So, how many particles are detected by D1 and D2?
So D1 was the detector on top, and D2 the one on left.
Okay, so what?
So remember your question, and we go on.
Okay.
The answers are given at the end of the test, so you keep a bit of tension. Good. We go back to the presentation. Yes.
No, there are 2 more questions. Stay okay.
Okay. So.
You can go back to the presentation and then click on the one.
Can I go on with the presentation?
No.
Then it's better to put them now.
Okay, so stay on page. I give the answer now. So, there was one person with the correct answer. This one. They are all detected by a single detector. The correct answer is number 1. we will go on why it's so. Okay, can we now go to the presentation?
So if you go to the presentation, go to the progress.
Okay, can we make the test at the end?
Sure.
Okay.
Go ahead.
Okay, sorry for that.
You can just go on the presentation
Okay, good. So, sorry for this interference that happened. So, this was the experiment, and these were the questions. And the correct question is they are all detected by D1, the correct answer. Now we make another experiment. We are in quantum land, remember, and we take cards. You see? They are normal cards, and they are half, say on average, more or less, they are half blue and half red, right? Nothing more. Now, what I do, I separate the blue from the red cards. So very easily I separate the blue from the red. Then I put the red cards aside and take the blue ones. So they are all blue, you see? All blue. Now, I turn the cards and they are mixed. They are half face cards and half numbered cards, more or less. So what I do, I separate the face cards from the numbered one. Okay. Then I put the face cards aside and take the numbered one only. Numbered cards. Test is ended. These are quantum cards. If I turn the cards, what's their color?
Which one?
That one.
This one?
Yes, that one.
I feel to be stupid.
No. Now, of course, as you have already the answer from the previous, maybe you may infer the question, correct, but okay, it's easy. We go on with another experiment now, right? This will be a bit more difficult because now we focus on this part here of the experiment. You see, here is a beam, blue light that comes in, and the two red beams comes out. So it's not a beam splitter. The beam splitter did not change the color. Green entered, green out. The color of the light beam is related to its energy. So what is actually happening here is at a close view up, I send a single photon with high energy and sometimes two photons with half of the energy come out. So not always, because not all single photons are converted in a pair of photons. So you have also, say, a violet beam. Now, the point is that these are photons. What are the properties of these photons? Well, now, suppose that instead of using photons of which we can measure polarization or frequency, wavelength, suppose we can measure just some properties of this and this photon, and we are going to do it with coils. So this is the blue photon. Danielle is the BBO crystal, and she gives me back a 2 euro. Now I take one coin up, and it's tail. Then the other one. Okay, tail. Then again with another photon. You give me 2 years. I'm not. not many pieces of 1 of 2 euro, but I give her 2 euro, she gives me twice 1 euro. Okay? I draw now the second one, and you see? Oh, sorry. Okay, believe me, it was a tail. Now I draw the second one. Okay, it's the same. Now I can draw them also at the same time. Great, and they are the same. Now the question is, I can do it thousands of times. Every time I give her 2 euro, she gives me 2 pieces of 1 euro. With these 2 pieces of 1 euro coming from the same 2 euro, so the 2 photons coming out from the same photon has been split. Whatever I measure, the outcome is always the same. Now, do you believe me or not? With the coins? With the photons?
Yeah.
By default.
By default. So, now we can make the questions. So, can we go now to the...
Do you want to do all of the questions now?
Yes.
Right.
So we have the... Because I have the answers now.
Okay.
So we
So you have to go back to Kahoot.it and now you go to answer all the questions
No,
again.
if you want to, we can do
So
it
2
again.
new ones and 1 that you already know the answer to.
And
So we can apply
ask
right
them
now.
to answer the first. So please answer the first question.
And they can answer correctly.
No, be honest. Answer the first question how you answered it the first time. So.
Out of the first one, so I don't have time to do anything.
I have one question to until everyone's in. Does everyone know what a photon is?
Yes.
So it's a particle of light.
Okay, but just to clarify,
Yes,
just in case.
I just, it's 1 euro. That you can
But we can have sense as well or not?
No, no, with photons, no. It's a quantum.
Yeah, I was
it's
confused because you presented when there is the split between of the beam.
Yes.
Between of the
But you cannot split it in 2 half photons. If you put the 2 detectors, you will always have only 1 detector clicks. So the photon or passes through or is reflected. It does not go half photon.
Impossible.
It's not the thing we don't get.
You have to refresh probably.
I leave it, it doesn't matter.
You
I
cannot
remember the answers.
Okay. Okay. Still people are coming? Doing?
Start.
Yep. So start. Are you ready?
No, I wasn't.
No, you have to apparently you have
So
to
here
answer
please be
honest.
I remember there was only 1 correct answer. So. You are using your animal and you are anonymous.
We'll let you do the stuff So if I turn the cards, what's their color?
So these cards,
The cards that are
where I took first the blue, sorry. Then I turned the cards and separated the face cards from the numbered cards.
okay. outcome of the experiment.
Yes, so for every €2 I give it to Danielle, and she gives me 2 pieces of €1. When they flip them, they are always the same, they have always the same outcome. Of course, it's a photon coming in. Great. That was not here. Okay. Good. Now, the correct... I should go back to the presentation.
Yes.
So we should now do the assessment, yeah?
Yes, now it's the assessment.
No.
SS.
Supersymmetry. There is a supersymmetric theory. So we have here quantum physicists of supersymmetry.
SS, okay, so we have the guy. Got 3 out of 3 correct. And then we have MM and cap. Of course, yes.
Oh, great. Congratulations.
Hope so.
The first one wins this side. Then the second one, the money.
Yeah, sure.
Okay.
Good. You will win the cards. The third one, the cards.
Okay, you can continue.
Tony, do you want to?
Okay, yes. Thank you. So we have. So there is one with a 3 out of 3, and 2 people with a 2. No, more than 2 probably. I don't know how it works. More than 2 people probably with more than 2 correct answers. So here are the answers. Here they are all detected by U1. Notwithstanding, this is a beam splitter, that if something comes from one, is a single photon, comes from this side, it splits, say, the probability of going left and right in 50%, 50%. Then here, the cards, not this one, but they're half red and half blue. Even if I selected only the blue ones at the beginning. And then here, yes, they have always the same outcome, always. Now, are you confused by this? Good. Here is the assessment of the questions. So, if you got 0 or 1 answer right, congratulations, you are a local realist. If you got 2 or 3 answers right, congratulations, because you are not a local realist. So, it's a win-win situation. Because you may be confused by the outcomes of the experiments, but you are in a good company. Because looking at some quotes by who made quantum mechanics, Einstein said that if quantum mechanics is correct, it signifies the end of physics as a science. Feynman said that the paradox, like Schrödinger's cat paradox, that it's dead and alive at the same time, is only a conflict between the reality and our feeling of how reality should be. Penrose said quantum mechanics makes absolutely no sense. And Schrödinger, worried about his cat, maybe now he apologizes. He is asking forgiveness to have had anything to do with quantum mechanics. So let's go quickly to the outcomes of the experiments. So the first one, why here all the photons are detected by D1? This can be explained mathematically with the mathematical formulation of a principle, the wave-particle duality. So the photon is a particle, but is a wave at the same time. What wave? It's an amplitude probability wave. It's a wave function. But say it behaves both as a wave and as a particle. And I see wave-like or particle behavior depending on what I decide to measure. So I have the detectors here. When the photon gets in here, it does not split half the photon goes one way or half the photon goes the other way. It cannot split. What happens is that the photon travels both paths at the same time. It's like a Schrödinger cat. It's in more than one places at the same time, or it's in no one of these places, because if I don't measure, I can tell. So, wave-particle duality. A particle that is localized in a place is the same as a wave. And the wave, if you think at a monochromatic wave or at the beach, a wave of the sea, it's everywhere. Wave-particle duality. Second experiment, indetermination principle. The point is that there are quantities that are complementary. Heisenberg's uncertainty principle says that one cannot determine at the same time some quantities like position and momentum. Momentum up to a mass is velocity. So suppose that in a card you have one quantity, but if you look at this, you cannot look at this one. When you turn, you are measuring the other quantity and you lose all the information about, you wipe out what is the color of the card. You wipe it out. It's not there anymore. There is no color, or it's both colors at the same time. So somehow you can say that if I measure the position, I lose all the information about the other variable, and vice versa. Entanglement. The last experiment to which the majority of you gave the correct answer is the most difficult to explain, because it's based on entanglement. Now, somehow with the card we have seen, okay, if I measure a system, I change its properties. But what if I would tell you that entanglement means if I measure this system, I change the properties of this system? So, you don't know the color, or you see that. If I measure this, the color here changes. And this is entanglement. Entanglement means that in quantum mechanics, for entangled particles like the two photons or the 2 euros she gave me, the two systems are connected somehow. And it means that the measurement of one system changed or determines the property of another system somewhere else, even on another galaxy, if the two particles are entangled. And this was a very difficult thing to accept for Einstein. So Schrödinger called it the characteristic trait of quantum mechanics. And polemically, Einstein replied it's a spooky action at a distance. It cannot be. Now, entanglement. What is entanglement? This is maybe the most technical definition in this short talk. Entanglement is a non-local correlation by which one knows more about the whole than about its parts. When I have the 2 euros that I entangled and I flip it, I do not know anything. There is no way I can predict if the outcome will be tail or head. It's local randomness. Physics has decided you cannot determine the outcome of an experiment. But if I take 2 entangled coins, globally I know what will be the outcome. They will be equal. So this is another concept. Now, all these experiments can be not explained, can be, the outcome of the experiments can be obtained mathematically, they are obtained in a lab, but what's the interpretation? An interpretation is not a theory. An interpretation is translating in words mathematical formulas. So one interpretation, the orthodox one, is by Copenhagen interpretation, orthodox interpretation by Borg, by the founders. And they say that a physical system does not have definite properties before being measured. The question, where is the photon, what path the photon has traveled before detecting it, makes no sense. You cannot ask it, because you ask the nature with an experiment, and you decide what the photon does, where it will be. Because the measurement causes a wave function to collapse. The second interpretation is hidden variables. now non-local hidden variables, because entanglement has been proved experimentally. So quantum mechanics is non-local, but still one could say the fact that the outcomes of these two coins is always the same is that the coin she gave me, when split in two, there is a set of hidden instruction to which I do not have access for some reason, that tells the coin what has to come out. Hidden variables. The problem with this interpretation that it's non-local. So the two coins or the two photons are identical without identity. They have not an identity by their own. Only the total has an identity. So they are more identical than twins could be. Then the last one, which is an interpretation that is somehow the most fascinating and intriguing, is the many-watt interpretation. So there is no wave function collapse. Simply, every possible outcome of an experiment pops up a new universe. So when I have my box and I open the box with the cat inside, in one universe there comes out, the universe splits in two. In one, the cat is alive, and in the other one, the cat is dead. If say you ask someone to go out for dinner, in one universe he, she said yes, in another universe he, she said no. Now, the most important thing is to be the one in the right universe, in this case. Good. Now, philosophy, experiments, strange single photons. We are talking about things that happen in lab. Who knows what strange things could happen there. But now let's skip 100 years. And we have New York Times, teleportation. People have used entanglement to teleport an atom. Quantum cryptography. In Switzerland, the state of Geneva is using since 10 years a quantum cryptographic system to protect the elections. The Economist, there is a race on quantum computation. Quantum cryptography markets now are something in which to invest. I should not say this, sorry, yes. And quantum simulators, so a quantum computer, a quantum system that simulates another quantum system, are used currently to design new drugs for medical applications. Now, even Ivanka Trump, 2 days ago, 2 weeks ago, tweeted that the Trump administration, with Google, you say Santa Barbara, has achieved quantum supremacy. Now, we will not be able to go through all the technological applications, but just two. One, quantum supremacy, because it's somehow a hot topic. What is quantum supremacy? Quantum supremacy means that scientists or industries, whoever is able to build a quantum computer by which one can achieve something that with an ordinary digital computer cannot be achieved. Now, this is Station Q. Well, it's a cartoon of Station Q, by which they have claimed to have achieved quantum supremacy. This computer has something like 53 qubits. What is a qubit? A bit is the elementary unit of information of a classical computer. A bit can be or 1 or 0, nothing else. A qubit is a quantum bit. It can be at the same time 0 and 1. It's a kind of microscopic Schrödinger cat. And people believe that if one has 50 to 100 clean qubits that work very well, then quantum supremacy is achieved. you can do with a quantum computer something that with a classical computer you can't do, like breaking cryptographic codes. All our security goes through a protocol when we do a financial transaction or we send a message over some social, goes through a cryptographic system. Our message is encrypted and then decrypted on the other side. The protocol we use is called RSA. How does it work in general? Say, I want to send a message to a recipient. I ask the recipient to give me a public key. With the public key, I encrypt my data. I send the data publicly, even on a newspaper, to the recipient, and the recipient uses his private key to decrypt it. Now, why can you not break the decrypted message you send publicly? Because somehow this system is based on the fact that public and private key are generated starting from choosing two prime numbers. And factorizing a product of two prime numbers is very difficult. It's called NP-hard problem. Computationally, it means that it's difficult to solve because, I mean, if I ask you the prime factors of this number, it's difficult. But it's easy to verify the solution, because if I give you the two prime numbers that multiply give you this multiplication can be done on a pen and paper. So, a quantum computer could crack it because classical cryptography is based on computational complexity, and if one achieves quantum supremacy, can break the computational complexity. But quantum mechanics comes to help altering this, because there is a protocol of quantum cryptography based on, say, the impossibility to know at the same time the number and the color. And so one can use this principle to encrypt the data. It's already used, and so it's physical, it's impossible to crack the message, to decrypt the message. Now, there is a big investment in this. The European Union has launched 2018-2028 a flagship, more than 1 billion euro, based on communication, computation, simulation, sensing, all quantum. What is aimed to achieve? At the very end, a universal quantum computer. But in the meantime, a quantum internet, quantum simulator, atomic quantum clocks and quantum sensors are already there. Now, how does Malta stand here? Malta stands here with this group, Quantum Malta group, where you already know Daniel. Yeah? Then two students making the thesis, Mirko and Jeremy. Two PhD students, one is here and you can ask him everything about quantum optics, he's an expert. Then Zold is a postdoc, me and our group leader, and if he were here you could ask him everything. So with this I go to the final. I hope that we make this small trip on a quantum spaceship, and we will go on discussing, and come into the quantum spaceship. But if you come, and I talk to students mainly here, this will be your life. So be aware. So if you want to learn more about some quantum mechanics without attending lectures, is Alice in Quantum Land, a fairy tale of Alice that goes to Quantum Land. Programming the Universe is a book by a quantum computer scientist, and then Anton Zeilinger made most of the experiments that I have shown before. Now, hoping that I did not induce you in a Schrödinger cat-like state of being scared and bored at the same time, I thank you for the attention, and I can proudly announce that the cat is alive.